So my name is Siri Mathisen. I work on in SINTEF Energy, and I'm part of work packages 3.3 and 3.4. Today, I'm going to talk to you about the strengthened Benner's curves in SDDP-based hydropower scheduling models. This is part of work package 3.4, which is the environmental constraints and uncertainties. So, hydropower scheduling, that's a complex problem, and we want to simplify it by dividing it into 3 levels. You have the long-term scheduling with a long time horizon and few details. Then you have the medium-term scheduling with a shorter time horizon and a bit more details. And then you have the short-term scheduling with a short time horizon and a lot of details. We will concentrate on the medium-term scheduling, and more specifically on SINTEF Energy's medium-term scheduling model, which is called PRODRISC. This is a combination of stochastic dual dynamic programming and stochastic dynamic programming. And PRODRISC is able to have a detailed hydropower description in an area, but if you include more areas, then you will get too long computation times. It is based on iterative forward simulations and backward recursions. And in the forward simulation, we see how the operation of a reservoir with respect to the generated strategy will be along historical inflow scenarios and price forecasts. Then we can use the simulation results as input to a strategy generation in the backward recursion. So stochastic models for inflow and price move recursively 1 week at a time along the scenarios to improve the strategy. PRODRISC will end after a fixed number of iterations, or if we have convergence for the income from the forward simulations and the backward recursions. The interface between the medium-term and the short-term models in SINTEF Energy is a set of cuts, and those are the strategies for the operation of hydropower plants. But this model uses linear programming, and we need a convex problem formulation to be able to have our cuts. Now let's look at each weekly decision problem, which is an LP problem. Here we want to maximize the profit of this week plus the future expected profit with respect to a set of constraints. Among others, we're talking about the hydro balance, which is the volume at the end of the week plus the discharge, which should equal the volume at the beginning of the week plus the inflow. From this constraint, we get a dual value, which is the water value or the slope of the cut constraint. This is the interface between PRODRISC and SINTEF Energy's short-term model. And traditional PRODRISC uses Benner's cuts, which is like one recipe for cut constraints. The cuts, they constrain the feasible area for the future expected profit for each reservoir level. So here you have the first cut 1 and cut 2, and in the end you have a lot of cuts, and they are forming a graph that is showing what the future expected income will be for various reservation levels. And the slope of these cuts, this is how much the expected future income will change due to a change of the reservoir volume. The cuts are produced in the backward recursion, but they are tested in the forward simulation to see if these cuts, if this strategy makes sense. But now to our problem. What if we do have a non-convex constraint? Say that we have this maximum discharge, which is dependent on the reservoir volume. So we have a reservoir, and if the water is below the threshold level, then we can only have a small discharge. However, if the water level is above the threshold, then we can have a large discharge. And we can see this in the figure to the right, that this is an instant change, and that is not very linear. We can model this using two constraints. First, we say that the volume should be larger than gamma, which will be introduced later, times the threshold volume, and the discharge should be less than gamma times a maximum discharge. And now we say that this smaller maximum discharge level is 0 for simplicity. This gamma variable is a binary variable. It's either 0 or 1. So either both of these constraints are active with a different number than 0, or both of them are 0. And since it is a binary variable, it will require a mixed integer programming instead of a linear programming problem. And in the forward simulation, we can interchange the LP problem with a MIP problem. But in the cut generation, we want to find the dual value, and we don't do that from the MIP problem. So now we may linearize the problem, assuming that gamma is not a binary variable. And then you get this constraint without the instant change in the maximum discharge. And now we can solve this problem with the traditional Bender's cuts. And the Bender's cuts, they are hyperplanes, which for only one reservoir volume will be a straight line. So the slope from the cut, that is a dual value from the hydrobalance in the LP problem. And the cut right-hand side uses the optimal objective value from the LP problem. And for this linearized constraint, we get a cut this spot on, as both the cut right-hand side and the slope come from the LP problem. However, in the actual non-linearized constraint, we see that the cut does not really constrain the future expected income. So we try this solution with strengthened Bender's cuts. So we still get the slope of the cuts from the LP problem, but now we get a right-hand side from the MIP problem that uses the non-linearized constraint. So this involves a change in the prod-risk setup as we exchange one LP problem with a set of first an LP problem and then a MIP problem. So the LP problem gives us the dual value, and the MIP problem gives us the right-hand side. Looking at how this was illustrated, we still have the same slope, but as we use a right-hand side from the MIP problem, we move the cut down to the actual nonlinear linear curve. And the slope is still not right, but the cut is placed at the right place. The consequences of this is that we are not using one LP problem anymore. We're using a combination of first LP and then a MIP problem. And besides, in the forward simulation, we will also have a MIP problem. And all of these MIP problems, they take a lot longer time to compute than an LP problem. So we're getting a huge increase in the computation times. But we'll get tighter cuts, and we'll get a decreasing, though not closing, convergence gap. And this was tested in a simplified model using a three reservoir area, which was resulting in a publication by Arild Helseth, Birger Moe, and Hans Olav Hågenvik in 2020. And the results there were a slight change in the operation of the reservoirs. These figures are showing reservoir 1 and 2, and also a better convergence. And here we see that the upper stippled line, that is the Bender's cut, and the lower steeple line, that is the strengthened Bender's cuts. And it's possible to use other types of cuts as well that might give better convergence, but also much higher computation times. And my work consists of implementing these strengthened Benner's cuts to the PRODISC model instead of to the simplified model. And I see that I'm over the time, so thanks so much for listening to me.